Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 1514, Path with Maximum Probability. This is a medium level difficulty graph problem. We're told that we're given an undirected weighted graph of n nodes. We're presented by an edge list and we're given two nodes, A and B, where A is the starting node and B is the end node, and or basically the edge. And we're also given a list of a probability of success. So each node has, or each edge, has a probability of success. And we're given two nodes, a start node and an end node, and we need to find the path with the maximum probability of success to go from the start to the end and return its success probability. And if there's no path from start to end, we have to return 0. And our answer will be accepted if it differs from the correct answer by at most 1e minus 5. So here's an example. We can see that there are two paths from start to end. So the start node is 0, the end node being 2. We can go from 0 to 2 with a probability of 0.2. Or the better probability is to go from 0 to 1 and then from 1 to 2. So that's 0.5 times by 0.5, which is 0.25. And that's a better probability of success. So we return that output, 0.25. And we're given a couple more examples. And the trick really to understand how we're going to solve this problem, as we've done in many other videos, is by understanding that whenever we have a graph like this, whenever we have a problem like this, where we need to find a path from one node to another node with weights, so in this case we've got probabilities, we use a little known algorithm called Dijkstra's algorithm. And Dijkstra's algorithm is basically breadth first search with either a min heap or a max heap. In this case, we'll be using a greedy max heap so that we explore nodes with a higher probability first. And so we're told that we've got an undirected weighted graph. So what's the first thing we do? Well, the first thing we do is we build an adjacency list. So let's do that. Let's say adjacency list is going to be equal to a default dictionary of lists. And we're going to say for I and get the A and B nodes for the edge in enumerate, and we want to enumerate edges, and we're going to say probability. So the probability is going to be equal to success or sucprob I, and then we can say adjacency list A dot append. And we want to append two things. We want to append B, and we also want to append our probability. And then the same thing for B. So we want to append A as well as the probability for that edge. And now our adjacency list is built, we can actually start doing breadth first search or doing Dijkstra's algorithm. So let's create our queue. So our queue is going to take in the start node, and that initially is going to be just a probability of 1, and the start node, we're just going to pass in start node. We want to have the max probability so far, which initially we can just set to 0. And we also want to have a max probability set, and this set basically is going to help us optimize our solution, and also indirectly prevent cycles, because we do have an undirected graph. And the way this is going to work is going to say, if we come to an edge and we know that we already have a probability which is better, we don't need to carry on traversing this path. We only traverse paths where we know we have a less than the probability that we already stored in our hash set. So we can say max probability set and set this equal to an empty set. And we're going to say while q. So while q q dot, actually let's take in the probability or the total, and we'll take in the node, and we will just say, let's just pop it from our queue. So we're just going to say q dot pop 0. Okay, so that's our queue. I'm going to say if our node is equal to the end node, then we can set max p equal to either what we have as max p or total. And then, as with any other breadth first search problem, we need to iterate through all the neighbors of the current node. So we're going to say for each neighbor and probability in adjacency list, and let's pass in our node. So what's our new probability going to be? Our new probability is going to be equal to the probability as times by the total that we've got so far. And then we can say if we already have the probability which is greater than our new probability, then we don't do anything, we don't traverse the path. Otherwise, we do want to traverse the path. So we're going to only traverse the path if max prob set, let's pass in the neighbor. Actually, no, we're going to say dot get neighbor, and by default we'll get 0 because it could be that this is the first time we've come across the node. If it's less than our new probability, in this case, we want to push to our queue the new probability as well as our neighbor. So we're going to say queue dot append, and we want to append total, or actually we're going to append new probability as well as our neighbor. And what we want to do next is say, let's set our neighbor node in our max probability set equal to the new probability. So we're going to say max probability set, pass the neighbor, and set this equal to the new probability. Okay, and that is our code done. That's our breadth first search loop done, and then we can just return max p. So let's check this code actually works. Okay, we get the tuple object has no attribute pop. Okay, so we need to convert this into a list, not a tuple. That's an error there. List.append takes exactly one argument. Okay, so we need to convert this now into a tuple. Okay, so this case, the sample test case is accepted. Let's submit our code, and our code is also accepted. However, you might have noticed that we're using just a normal queue, and this isn't Dijkstra's algorithm. This is just basically breadth first search. So how can we change this? Well, we can make sure this is instead a heap. So we're going to say heap queue.heap pop and pass in our queue. And we can also say heap queue.heap push. So heap queue.heap push and pass in our heap as the first parameter. But there's a little caveat here. So Python uses implements a min heap by default. So what we want to do to get around this is convert all of our probabilities to negative values. We're going to set this equal to negative probability. And then we can say negative probability equals, and then we want to flip this around to a positive probability. So we're just going to say, actually, let's set total equal to minus negative probability, which is going to make the negative positive. And then again, here we want to pass into our heap a negative probability. So it's a little hacky, but it gets the job done. Let's say heap is going to set this to queue. And let's submit our code again. And we pass all 21 test cases again. So this is just a more optimal solution using Dijkstra's algorithm. So I hope you guys enjoyed this video. In terms of time complexity, we're looking at, and again, this can be debated, but in a worst case scenario, we're going to say E log V for time complexity. So I hope you guys enjoyed this video, and with that being said, I'll catch you in the next one.